So this is over all the sections we've done so far. Now, I broke down 1-1 into a few pieces, A, B, and C, and 1-2. So it covers lots of sections. I didn't want to go on to 1-5 until we had a test over 1-1 to 1-4. So the test will be Thursday. It's going to look like this. Now, the first thing says, determine whether each relation represents y as a function of x. Okay? So what are functions? If you can get it to look like f of x equals all of the x's, that's a function. If the x's are only paired up once. If I plug in an x and I only ever am going to get one thing out, that's a function. So this one right here is technically a line. It is a linear function. So ax plus by equals c is linear. Y equals mx plus b is linear. So as long as you have a y in the equation and the x and the y are just plain old x's and y's, there's no powers, there's no nothing, this would be a yes. Now, when it comes to number 2 with a listing of points, all we have to check are the x's all different, because that means they were only used once. So every single x is different. We do not care if the y's repeat. We do not care if the y's can repeat a million times. But as long as the x's are all different, that one's a yes as well. Now, for graphs, we can use the vertical line test. Okay, so if
Go back up to number 2, Mom.
Yeah, so number 1 is a yes, number 2 is a yes, because 2 is a yes because the x's are all different. So if the x's repeat, it's not a function, but y's can repeat as many times as we want. Now 3 and 4, we can use for a graph what's called the vertical line test. If we can find a vertical line that hits the function more than one spot, like this one does. All we have to find is one time that happens. You can find lots of times on this one, then we get a no. But number 4, no matter where I draw a vertical line, I only ever hit it one time, so that's a yes. So functions, the x's do not repeat or pair up more than once. Okay, so if you look at the graph, if you find a vertical line that hits it twice, it's not a function. If every vertical line you could possibly think of always just touches it once, then yes, it's a function. Does that make sense for that?
Yes.
Okay. Everybody good with those?
Yes.
Okay. Now, the next thing we're talking about is piecewise functions. You will need to have to plug into a piecewise function, okay? So I'm going to add a little bit to this. Let's find f of 1, f of 2, and let's do f of 3. Okay? Now it depends on what value you're looking at as to where you plug it in. So always read your function over first. So this says that for any x value that is less than 2, we plug it into here. For any x value that is greater than or equal to 2, we plug it into there. So you have to be careful. So 1 is a value less than 2. So we plug it into that top function. So it's 1 squared plus 3 times 1, which is 1 plus 3 or 4. Okay, so for this particular function, where do we plug it in? Well, 1 is less than 2, so we plug it into the top function. 2 is on the border, but the equal to part is there, so we plug 2 into that one. It's just 2 plus 10, or 12. 3 is greater than 2, so it goes into this one as well. So we're going to use that one more time, and that's 3 plus 10. Or 13. Okay, so just where's your border, which you only use one piece at a time, unless you're checking continuity. It's just, I plug 1 into the top one because that says where I plug in x values less than 2. I plug in 2 into the bottom one because it is the equal to 2, and then 3 is greater than 2, so it goes in the bottom as well. Do we understand how to plug into a piecewise function? Okay, let's take a look at 6. 6 says that during a baseball game, a batter pops up the ball to the infield. After t seconds, the height of the ball in feet can be modeled. So what you got to remember is that t is seconds, and h of t is feet. So it's just, just reading and interpreting what they're telling me. If I plug in seconds, I get out feet. H of t is feet, t is seconds, okay? So for A, it says, what is the baseball's height after 3 seconds? So that's a t. Remember, t is 3. Okay, so all we got to do to answer A,
Plug in 3.
yeah, plug in 3, you got it. So it's just negative 16 times 3 squared plus 50 times 3 plus 5. Okay, 3 squared is 9. So that is negative 16 times 9 plus 50 times 3 plus 5. And once we've done that power, you just do your multiplications. So negative 16 times 9 is negative 144. 50 times 3 is 150. And then we just combine them. Negative 144 plus 150 plus 5 is 11. And then we should put our units, because remember, if we stick in the time, we get out feet. So that means that after 3 seconds, the baseball is at a height of 11 feet. Now, I'm not too concerned.
How slow is the baseball going?
Huh?
How slow is it going?
I don't know. Maybe it's more of a line than way up high. I don't know. And then in B, I'm not as concerned about that, okay? But I do just want to talk about it for a minute. For something like time, do we use negative numbers? No, we don't go backwards in time. We don't have a time machine. And so the domain or the t's would start at 0 and kind of go to infinity, but in a way it kind of goes until we hit the ground. But I would say if you just put infinity, whenever it hits the ground, it's not going to go through the ground and keep on going. So a parabola in a real life setting is where does it start and where does it land or hit the ground, okay? But without doing a calculation, we'll just leave it there. Now, how could you find the calculation if you put that into Desmos? Instead of using t's, just use x's. You can see where it hits the x-axis. That's its landing spot. You could figure that out if you wanted to, but I don't really care. Okay. Is everybody good with 6? Okay. So for ones like that, I will focus on the test on something like A, not the next. Okay. It says for 7 and 8, we want to find the y-intercept and the zeros, and then find these values algebraically. Now, I will tell you, from the book I got these from, the graph isn't always a perfect representation of what they have. I don't know why but, okay. But I think these graphs are good. So let's find them from the graph, and let's find them algebraically, okay? So to find them from the graph, the y-intercept for this one is 0, 0. It's the only place we hit the y-axis. Functions will have at most one y-intercept. So where you hit the y-axis, that's your y-intercept. Zeros are just a fancy way of saying x-intercepts. So you're just looking for where do we hit the x-axis. So we can put a little dot. Now this is one that's kind of unique. It has an x-intercept and a y-intercept at 0, 0. So we can write 0, 0 again. Then we have negative 4, 0 and positive 4, 0. Okay. So that's how you find it from the graph. So there will be one at least that I throw a graph on there and say, what are the intercepts? What are the zeros? And then you would do that, okay? So let's use 8 to do the graph as well, okay? So it appears here that our y-intercept is at 5. So you see the y value is 5. So that's the 0.05. It only appears that there is one x value, or x-intercept, or 1, 0, or whatever you want to call it. And then I believe it's 25. So that's a y value, I'm sorry, a y value of 0 and x value of 25. Now, let me write down these equations, and I'll show you that again. What was that one? Okay. So does everybody see how to get that from the graph? Do you guys see how to get that from the graph? Where do you hit the x-axis? That's your x-intercepts or zeros. Where do you hit the y-axis? That's your y-intercept. Okay? Now, it does say to find them algebraically, and that's one of the skills I really want you to work on. Okay, so let's look at 7 and 8, and now let's do the algebra that finds the same values we saw before. Okay, the easiest one I always thought is the y-intercept. You just plug in 0, so that's an easy number. Okay, so you just plug in 0. Remember how we got the 0.00? So it should happen again. If you plug in 0, you get 5 minus the square root of 0, or 5. And we did. We were hitting there up there at 5. Okay. So the y-intercepts are easy. You just plug in 0. Don't overthink it. You only should ever have one value. Sometimes it's undefined, but most of the time you're going to get a y-intercept. Plug in 0. What do you get? That's what you get. Okay. The x-intercepts, or the zeros, you let f of x equal 0. Okay, so you actually set the function equal 0. That's the y equals 0. So however you want to think about it. So we're going to make this our 0. We're going to make this our 0. I don't write 0, do I? And you'll notice the only thing is an x. We're looking for an x-intercept. We're looking for a 0. Okay, let's do the first one. To solve something like this, factor it. See how they both have an x in them? That means I can take out an x. Okay, so they both have an x, so we can take out an x. How do you factor this part again? You remember how to factor x squared minus 16? Do you remember how to factor x squared minus 16? You got it. So it's just the difference of squares, x plus 4 and x minus 4. So factoring is the key to solving for the x-intercepts of a polynomial. Factor it. You can use a quadratic formula if you get down to a quadratic phase and you don't remember how to factor it. And then you set each piece equal to 0. Now, if you recall, in the graph, it hit it 3 times. And so we got values of 0, -4, and +4. And that's what the picture showed us. We had 3 of them. Now, 8, we should only get one value. Let's check. I'm going to take the negative square root of x to the other side to make it a positive square root of x. What gets rid of a square root? What's the opposite of that? The opposite of a square root.
A square.
Yeah, it's a square. Don't overthink it. It's just a square. So we're going to square both sides. And you might recall that the value we got was 25. And so that's where it hit the x-axis. So your algebra and your geometry should always go together. I will probably give you a graph where you have to find it by looking at the graph, and then I'll give you some equations you have to find it algebraically. Okay, so you do need to know both. We good with 7 and 8?
Yep.
Okay, so that's 7 and 8. Now let's go back up to 9 and 10. Put a big X through 10. I don't care about that one. That's a step function, sometimes called the greatest integer function. We're going to explore that in 1.5 a little bit, but it's one that doesn't come up too much, so it's not my biggest concern. I want to talk about this one. Okay. So the domain and range of a function by looking. Remember, the domain are the x's that are used from left to right. The range are the y's that are used from the bottom of the graph to the top of the graph. That's the best way to think about it. What x's are used from left to right, what y's are used from bottom to top. That's the best way to think about it. So what is the smallest x value we use for number 9?
0.
What's the biggest x value we get to use? Yeah, we're going to keep going to the right. So that arrow indicates infinity. So the domain would be from 0, probably in a bracket, because it looks as if it's just a point, to infinity. Okay. The range are the y's. It just so happens the lowest point is 0, and the highest point is infinity. That doesn't always happen that they're the same. That's kind of a unique case, but that's what happened for that one. Okay. So I will give you a graph. You will have to tell me the domain and range. The domain or the x values go from left to right. The range or the y values bottom of the graph to the highest point, the top of the graph. Everybody good with that? And again, we're going to practice one more time tomorrow before the actual test. Okay. Now let's go up here. It says determine whether each function is continuous at 5 and justify your answer using the continuity test. Okay. So the first thing you should always do is, first step, can you plug in 5 and you get a number? Because if you can't plug in 5, it can't be continuous there because it means it doesn't work. If you plug in 5 to this one, you get 25 minus 36, or the square root of negative 9. Is the square root of negative 9 a legitimate number? Is the square root of negative 9 a number? Well, can you take the square root of a negative? I mean, we can get an answer, but would it be a real number? No, remember, square roots of negatives are the I thing. This is actually 3i. So it's not a real number. So you would say it's not continuous. Now, what's interesting, if we look at the graph of this thing, I think, this is just off the top of my head, but I think this has like 2 little wings, and it kind of has, there's nothing at 5. So how can it be continuous at 5? Because there's nothing there, okay? So looking at the graph is helpful as well. If you plug 5 into this graph, you get 25 over 10, which is a number. Doesn't matter what the number is, it works, it's continuous. If we were to graph it, and we were to look at that spot of the graph, there's a perfect little section of the graph there. The only value where there's a vertical asymptote for this one is negative 5. 5 works fine. Everything else works fine. But negative 5 is the only value that doesn't work. So remember, a function is continuous if it works at that spot and the graph lines up perfectly right by that spot. Okay. Now let's look at 13 and 14, end behavior. So when they say end behavior, I like to color in the ends of the graph. Okay. And the reason I like to do that is because that's what you're looking at. Okay. So the left end and the right end, we're describing the height at the ends. The height at the ends, okay? So the left end height, as x goes to negative infinity, the y is going to positive infinity. It's going up. Up is positive infinity. On the right, as the x goes to positive infinity, the y is going down to negative infinity. So it's just saying on the left end I'm going up, on the right end I'm going down. So that's the most efficient way to do it. If you know that limit notation, you can use that too. It doesn't matter. This one's kind of weird. Do you see the equation here? Let me put some information. There's a little tiny asymptote right here at x equals 5. No, that would be y equals 5, I'm sorry. So both of these ends are heading to 5, and the reason they're doing that is because we have 1 over x, which as we get really large goes to 0, and 0 plus 5 is 5. And so this is a unique one. As x goes to negative infinity, the y is heading to 5. As x goes to positive infinity, the y is heading to 5. So the ones that have like the two pieces heading outward, you're heading to a value, in this case 5. So that's that. We're almost done, I know. It's not fun, but, okay, 15. It says f of x contains a discontinuity at 3. Do you see how there's an open circle and it's closed in at a different spot? We would have to jump to that spot. That's a good way to remember that. Or I'm sorry, if the pieces are separated, but here there's just a hole in the graph that we have to leap over, a hole. So this is removable. This is hole. This is a vertical asymptote, and this is a separation. So this particular one is a hole. We didn't really do that one, okay? So in that particular case, if there's a hole in the graph, it's a removable discontinuity. If there's a separation in the graph, that's a jump. If there's infinite, it's a vertical asymptote. And then we'll go over that more next time. Okay. 2 more, or 3 more, and then we're done for today. Okay. So this is that increase and decrease you saw on your practice yesterday. Okay. So I would suggest that you think about the math book here. The math book's right here. See how he's going downhill. So I think it's a good idea to kind of color code. If it's going downhill, I'm going to make it red. Once he starts going uphill, I'm going to make it green. And that looks like it's possibly at a value of about 3. Okay? I think the x value, let's just assume it switches over at 3. Okay? So for an x value from negative infinity up to 3, we're just going to call it 3. Just if you're given a graph, just guesstimate, but I think it's 3. The y is going downhill, which we call decreasing. For an x value from 3 to infinity, that's what I've highlighted in green, the y is increasing. Okay, so this just says for this particular x path, my bug's going downhill. And the second one says for this particular x path, my bug is going uphill. See how that works? Now, for 17, my bug has to really travel through 3 different phases. So he starts going uphill until I think an x value of -2. And then he goes a big downhill path. And that looks like, I don't know, it's not quite 2. So we'll guesstimate +1. And then he goes uphill again. Okay, so we have 3 paths. So from negative infinity to an x value of -2, my bug is going uphill. So from negative infinity to -2, for those x's, he'll go uphill. And now from an x value of -2, and it looks like this one is about here. We'll say a +1, but I don't know. And then he's going downhill. And then from 1 to the rest of his little life, he's going uphill again. So see how there's 3 distinct sections of the graph. That my bug is going uphill here, downhill, and then uphill again. The interval is talking about the x's where that happens. The word is saying what height is happening to the bug. Is my bug going uphill, downhill, or flat? Okay, one more. The height of an object dropped from 80 feet above the ground after 2 seconds is given by that equation. What is the average speed for the object during the first 0 seconds? See the words here, average speed? That's the stuff we did in 1.4, okay? So if you think about, it's really just saying what is happening on the interval from 0 to 2. So we're averaging out what happens at 0 and what happens at 2. If you plug in 0, you get 80. So that's the point 080. If you plug in 2, you get negative 16 times 2 squared, or 4, plus 180, or plus 80, is 16. So that's the point 216. So we're just doing the that average value formula, the slope equation, however you want to think about it. So remember, it's y2 minus y1 over x2 minus x1. Okay. So the first one you plugged in, 0, let's make that x1, y1. And your 2, make that x2, y2. That's the easiest way to approach it. Okay, so that would be 16 minus 80. That's the difference of the y's. And then 2 minus 0 are the difference of the x's. 16 minus 80 is negative 64. Divided by 2 is negative 32. So in physics, when you drop something, that negative is indicating you're getting closer to the ground. So kind of it is somewhat directional, that the negative is indicating we're getting closer to the ground. The 32 is the average, that would be feet per second, because you plugged feet in here. This is feet, this is seconds. So that would be feet per second. Okay, so turn this in. You need to study between now and the test on Thursday. So I'll post this video. You can watch this. Going backwards and looking at any of your notes from before is also helpful. But there's, as you can tell, a nice chunk of stuff on this test, okay?